Hi, my name is Allison Wilcox, and I am a senior in biomedical engineering. For my honors capstone project, I worked with Michigan Neuroprosthetics design team on our 2020 design cycle.
Michigan Neuroprosthetics has identified a need for a cost-effective upper limb prosthesis for children. Over 2,500 pediatric patients have an upper limb reduction, which leads to an average lifetime cost of over $1 million. Additionally, there's a discontinuation rate of over 20%. That is, people who have a prosthetic but have stopped wearing it for reasons such as comfort, usability, or other various reasons. At Michigan Neuroprosthetics, our mission statement is to design these cost-affordable, accessible, and scalable myoelectric prosthetic devices for pediatric patients. Our arms are affordable because they can be produced for under $200 each, and we provide them pro bono to the family. They are lightweight because all of our models weigh under 1 kilogram, which is far lighter than the average prosthetic in the market. They're customizable because we work directly with the patient and their families regarding their desires for the product. And finally, they are scalable because our 3D printed model means that it can be easily reprinted as the child grows. Our arm is controlled by two motors that connect to strings that run to the tips of the fingers so that when they rotate, they pull the fingers into flexion. One motor controls the thumb and index finger, and the second motor controls the middle through pinky finger. The arm is neurally controlled because we can detect muscle impulses on the bicep, which we use to control flexion of the hand. For our 2020 design cycle, we continue to work with our client from the previous year, gaining feedback on our last prototype. We established a number of design goals from those user needs, as well as some that we defined based on our need to make a more easily assemblable arm. One of the challenges of assembling the arm is stringing the hand, so we wanted to redesign the palm for more ease of stringing. Additionally, we wanted to add a charging port to the arm so that the client did not have to open up the lid of the forearm and manually take out the battery to charge it every night. Simply, they could plug the arm into the wall. Next, we needed to strengthen the forearm socket interface. Our last prototype broke at this interface when it fell off the client's shelf. This was not a failure mode that we had previously predicted. However, this is obviously a weakness in our design that needs to be improved. Overall, we wanted to improve the aesthetic appearance of the arm and reduce its weight. First, we started by redesigning the hand. On the left, you can see the previous hand where the knuckle joints were quite rough and angular. Now, we redesigned it so that they are quite smooth and filleted and have a higher aesthetic appeal. For the string channels, you can see that previously the channels merged very high up in the palm. Additionally, there was a strange lip that the strings tended to get caught on while we inserted the strings. Because the channels merged so high up, the strings had a tendency to tangle, which negatively impacted the grip strength. So, after our redesign, the channels merge very close to the end of the palm, and there is a smooth transition from the channels into the forearm cavity. We recreated the forearm model completely from scratch this year. Previously, we had simple cutouts for the battery and motor compartments, which didn't leave a lot of space for wire management and the circuit board. Thus, as a last-ditch effort to get all the components to fit while we were assembling the prototype last year, we had to add this rectangular bump to fit everything. A major goal this year was removing that and making sure that all the components fit smoothly. Now the arm is designed with additive principles in mind so that there are only supports directly where they are needed for the different electronic components. Additionally, we worked directly with the electronic sub-team to create a slim printed circuit board design that fits snugly at the back of the forearm. One of the main desires of our client was to feature a charging port in the new forearm design so the battery did not have to be removed every night for charging purposes. We were able to meet this request. You can see the channel here that exits on the side of the forearm. We used a plug to cover the forearm cavity during the day so that accidental water splashes could not harm the electronic components inside. We then moved on to redesigning the joint between the forearm and the socket. Although COVID-19 prevented us from doing any in-person physical testing, we were able to use finite element modeling in the Fusion 360 package to test our various designs. We used a 3-point bending setup where the arm was supported on both ends and a load was applied to the middle at the interface. Seen here are two of the designs that the team came up with. We were looking to minimize the stresses on the outside rim of the interface because we hypothesized that the interface failed due to crack propagation that started at this outside rim. Thus, the design on the right featured lower stresses on the outside rim. While there are higher stresses on the inside cavity, we do not believe that this will lead to a failure mode of the socket detaching from the forearm. Likely, those higher stresses are a result of sharp corners that finite element models do not handle very well. Overall, all of these design changes resulted in a weight reduction of 8%. While we had hoped to reduce the weight even further, upon analysis, we realized that the vast majority of the weight was coming from the electronic components, which could not be weight reduced any further. We do still have room for improvement in reducing the weight of the socket and the tricep cuff, and these will be focused on in next year's design cycle. In conclusion, we were able to meet all of our design goals for the 2020 design cycle. While the ongoing pandemic proved a challenge for prototyping and manufacturing, we were able to deliver our prototype earlier in November. We will continue to get feedback from our client about what needs to be improved for the next design cycle. The unique experience of working completely remotely for the second half of 2020 gave me the opportunity to take a deeper dive into finite element analysis that I otherwise wouldn't have gotten, so I'm grateful for the experience that this project has given me on that end. I want to extend a huge thank you to the rest of Michigan Neuroprosthetics, especially the other team leads, as well as our faculty advisor, Dr. Chestek, for her guidance throughout this project. If you're interested in learning more about Michigan Neuroprosthetics, you can check out our website or send us an email. Thank you again for your time and attention, and have a great day.